Hello everyone, welcome to week 5, COMP9417 tutorial. Let's get started. So today we'll be going through decision trees. That's a pretty fascinating area in machine learning. It's arguably the most popular machine learning algorithm in the wider world in industry, if not decision trees, then ensembles of decision trees, which we'll learn about later in the course. Things like random forests, the very popular gradient boosting machines, so on and so forth. But yeah, decision trees are very popular, right? Yeah, so cool. So I'll go through the basics, pros and cons. I'll talk about your classification trees versus your regression trees, how they go about doing their splits, a bit of a chat about overfitting. Then I'll talk about the tutorial questions, and then the Jupyter notebook, as per usual. All right, cool. Yeah, so let's talk about decision tree. What is it? So, I mean, in contrast to, what have we talked about so far? We've talked about, linear regression, logistic regression. We've talked about your naive Bayes classifier, your basic Bayes classifier. We've talked about k-nearest neighbors. We've talked about your nearest centroid, nearest medoid classifiers. And they're all a little different to this decision tree. The linear regression, it's a line of best fit, and it's got a probabilistic interpretation as well. When you minimize the sum of square errors, the probabilistic interpretation being that the errors are Gaussian or normally distributed. Naive Bayes, it's got some statistical assumptions behind that. It's got a probabilistic framework, of course, your naive Bayes assumption that the distribution of the features given the target, they're independent, right? And then your things like your k-nearest neighbors or your nearest medoid, nearest centroid. Yeah, so those treat all your features as, I guess, dimensions in terms of distance, and then you look at some sort of measure of distance towards different class centers, or I guess examples which are similar to whatever you're trying to predict. Decision tree is a little different to that. Decision trees are essentially a bunch of if-else statements. I think to me that's the easiest sort of way to go about it. It's, imagine if you were trying to just you have a table of data and you're trying to just create a bunch of if-else statements that separate the data, and it allows you to create some sort of prediction. So for example, let's say you had a table of data and a fish, a salmon or sea bass, and you want to create a bunch of if-else statements to separate them into either your salmon and the sea bass. And of course, you want a good degree of accuracy. You want your if-else statements, if you get to the end, you want it to be correct. But also you got to balance that with not having too many if-else statements. So I'm hinting at overfitting here, right? So the more if-else statements you have, the deeper your tree is, the more complicated your model is. Yeah, you have less bias, but yeah, you got more variance. You have more variance. And that's not necessarily a good thing, and you could be overfitting, right? So let's walk through this example here, and this is a simple example. So if you have the data in tabular form, it might look something like this. You have your first feature, you have your second feature, and then you have your target, and you might have, I don't know, say 30. Let's call it. 30, and then I don't know, 40, and then let's call this salmon. Let's call this the positive class, and let's call this the zero class, right? And then maybe next one you have 25. I don't know, I'm making up 60, and there's a 0, and there's a 1. Maybe there's a 55, and there's a 20, a 15. I'm making up, but your data in tabular form might look something like this, and your decision tree, you kind of want to the algorithm's kind of thinking to itself, okay, how do I create a bunch of if-else statements to separate this data the best, so that I can have some sort of y hat, and hopefully the prediction is good. The prediction is the same as what the actuals are. Again, hat being prediction here. Okay, so if we were to plot our data, it would look something like this. So again, let's say one is salmon. So maybe there's some point here. I don't know. Let's call that 50, and then let's call this like 20. So maybe I'll change it to this example. So maybe that's the first observation. That's that. Yeah, maybe I should change these to something more realistic. And then maybe have, I don't know, let's call it 60 and then say 15. Oh, 60 and then say 15 here. And then maybe this one could be, say, let's call it 10 and 50. Something a bit more realistic or a bit more congruent with, so that this table is a bit more congruent with this graph here. Right. So this is what the data looks like, and you effectively want to create an algorithm to separate your red guys, your salmon, from your blue guys, your sea bass. I've seen a few ways to do it. You could fit some kind of logistic regression model, and it would effectively, you'd have some sort of threshold where there's some point where the probability, let's call this a probability of it being, say salmon is 50%. This is maybe a decision boundary, right? And you have some linear sort of separating line here, right? That could be, say, linear regression. If you did a basic linear classifier, it might be something like that. Might be something like that as well. So I'm going to call this one logistic regression. I'm going to call it log reg. We could have also, say, done some sort of a, I suppose, k nearest neighbors approach, and maybe not k. K nearest neighbors approach as well. And you probably have a bit more of a jaggedy sort of decision boundary. Of course, the k nearest neighbors, you put in a new example, say here. Let's say this is a new example, you don't know what it is, and you just find what are the nearest neighbors. Let's say the k is 3, and the 3 nearest neighbors are this guy, this guy, this guy. You take the majority class, and you say, okay, I'm going to predict this guy as a triangle, which is the salmon, right? Could have done that. You could have also done the nearest centroid, so maybe the triangle centroid is, let's call it here. So maybe that's the, I'm just going to call it mu. Let's call this the salmon centroid. Right, so sort of the middle, the average of both dimensions, and maybe something like this could be the centroid for your sea bass. Right, and then you make your prediction that way. But that's not how we're doing here. We're doing a decision tree, right? And what the decision tree does is, and let's just step through this, is, as I said, it's a bunch of if-else statements. So in our algorithm here, let's say we have a new example. I'm going to call it, let's say we have a new example here, and we don't know what this is, right? And maybe let's just also say it's sitting at, let's call it 70 and let's call it 70 and 40, let's say. Right? So if we feed it through this algorithm, right? So now we have our new example here, which is 70, 40, and our question is, okay, it's cool, but what is our y hat? We'll go through this, right? We'll go through our decision tree. Is x1 greater than 80? No. So we'll go down this sort of path, right? And then it's x2 greater than 10? Yes. So the prediction there is sea bass in this case, right? So in this case, it'll be class 0, right? And of course, you go through more examples in other sorts of ways, but this is effectively how the decision tree classifies things. And one thing to note, though, is that this isn't perfect in that these at the bottom, are the predictions at the leaf node, but it's not always correct. It's not perfect. So along the training data, right, you can see there's a few misclassifications. So I mean, this one is this is an example here, right? So in the decision tree, it's perfectly classified everything except this one here. There's this one data point which is, it's set at sea bass, but it's really salmon, right? So the accuracy there would just be well, there'll be one off. It'll be whatever that is as a percentage of the entire data set, right? But still it's quite good here. I mean, the accuracy be 90-something%. Say it's still quite good, but just keep in mind that at least in this example, it's not perfect, and possibly what you could do is maybe you it might actually it's this one, isn't it? Yeah, I think it's this point. So this looks like this point. So this little guy here is this little guy here. You can probably understand why it's misclassified because it's just so out of character, right? But if you let this tree just go on and on, you could possibly create, some more splits, that ends up with, say 1, 0, and then say 0, 5. You could possibly end up with some splits and then perfectly classify this, right? Maybe you just, so here we go. Here's what these splits look like, right? The first one is, is x1 greater than 80 or not? So that's this split here. And then, the next one is, let's say it's less than 10. Sorry, let's say it's less than 80, then is x2 greater than 10. So then, that's sort of this partition here is I guess, greater than 10 is this partition there, right? And there's 4 CBAS, etc., etc. You could artificially, maybe I shouldn't say artificially, but you could create some more splits, and it probably would be a bit, what's the word? It probably would be a bit force. It will be definitely forcing. It'll be overfitting, right? Let's say you were to create another split, then you say, what if x2 is, greater than whatever this amount is? Maybe you split along here, right? And then again, this is contrived, but then maybe you want to split along here as well. So then what you would have is you'd have, here you'd predict CBAS. Here you predict salmon, CBAS, salmon, and then if you create this little, I guess, forced overfitting kind of split here, maybe 2 more splits, then it'll be perfect. But this is overfitting, right? And that's one of the issues that you find with your decision tree. It's very, very easy to overfit. Cool. I hope that gives you a bit of a flavor as to the classification tree at the very least. There's a couple of questions here. Just a bit of a refresher about how trees in general. The tree data structure in general, not just a decision tree in the machine learning sort of context. What is the root node? What is the root node? Just this guy here, the one at the top. What are the leaf nodes? Leaf nodes are the guys at the bottom. So this is basically a tree upside down, right? The roots at the top and the leaves at the bottom. What are the predictions? So typically what happens is, when you do these splits, the prediction would just be the majority. So it'd just be the mode, at, it's a funny outside, mode at the leaf, right? So once you do all these splits, right? So in this example here, right? Each of these splits, you look at the mode, and that's your prediction. So for example here, your y hat will be equal to CBAS, which I coded as 0. Here, your y hat will be 1. Here, your y hat will be 1. Well, these are obvious because the majority, well, there's only one of these, each of these, but this one, the majority class is your blue, which is your CBAS. So the predictions are the mode, or I guess the majority vote, or the majority vote at the leaf node. It's a bit messy, isn't it? There we go. Can we use logistic regression for this? Yes, we can. So as I spoke about before, we there's a couple, you can use any classifier for this really, but the ones we've covered so far, we can use logistic regression. We can use k-nearest neighbors. We can use your nearest centroid, nearest monoid. I mean, they work a little differently, but no reason why not. With your logistic regression, what would effectively happen is, if you want to draw, you have to kind of do it you'd probably want to do it in 3D, because you'd effectively have a decision kind of surface, right? How do I visualize this? You have a z-axis, which would be, I guess, the y prediction, and if it's say salmon, you code it as 1, so it goes straight to the top. If it's CBAS, you code it as 0, so it goes to the bottom, right? And then you sort of fit this sigmoid shaped, sigmoid sort of a curve planey sort of thing to that, right? And that'll give you your probability going from 1 to 0. Or you could just draw it in 2D and you have some decision boundary where y hat is equal to 50%. But yeah, you can use logistic regression for this. Cool. So let's talk a bit about the some pros and cons of your decision trees. So as I say, it's one of the most popular, arguably the most popular algorithm in machine learning, depending where you work. If not decision trees, then I guess derivatives of it, say ensembles, things like your random forest, and of course your GBMs, which is what I'm thinking about. Very popular. There's some pros about it. They can be interpretable and easier to explain. So something like this is quite, I guess, without going too much into detail, it's not too bad to explain, and arguably, this is easier to explain to someone than linear regression. You just draw like a flow chart on a whiteboard, and you can kind of explain to them how a decision tree works. So that's where you get interpretability. Now, of course, you lose this. It's not the case. It's not the case for ensembles. Then it's kind of the reverse. If you have some ensemble, like, and we'll talk about later on, of say 1,000 stump trees all boosted together, it's not going to help your interpretability. There are ways to interpret, your ensembles and some cool things out in the world that are quite nice. Things like you can look at, your feature importances, like Gini feature importances, to work out which features are, I guess more used or more important. One of the difficulties often with ensemble methods is how to interpret the features. Often you want to see, what we call, say, the pure effect of a feature is. And what I mean by that is, if you were to just look at one feature in isolation and work out what the impact is on the target, what does that look like, right? What does that shape, right? There's things called partial dependencies, which are, again, it's not part of this course, I'm just going to stress, but one of the problems historically with machine learning is you lose model interpretability. So if someone says to you, okay, that's great, but I'm curious about this feature, what's its impact on the target? There's not a direct way with decision trees, but partial dependencies allows you to sort of break it down. So I'm just going to use insurance as an example again, because I'm familiar with it. But let's say this is some measure of claims frequency. So this is the target, and it is context. Let's say this is context of motor insurance, right? And yeah, so this is a very typical shape you might see in motor insurance. So let's say this is maybe this is, say, I don't know, let's call it a 25, right? And this will be what you might call the pure effect, right, of age, the feature age, right? So the idea is that the young drivers are quite bad, and they get better as you become an older driver, and then as you get older and older, your reflexes, your eyesight, all that sort of goes away, and you become worse again. I'm exaggerating on this end, but anyways, something like this. So this, you can actually use something called a partial dependency to sort of interpret some of these more black boxy models, and they're quite powerful. Now these sorts of, I guess, partial dependencies, they come free of charge in linear regression. In regression land, this is you get an equation. it's defined, right? So in linear regression land, right, you might have something like this. I'm just going to make it up. And then maybe you have, like, let's call it beta 1, and let's call this x age squared plus beta 2 x age. So if you were to fit some sort of linear regression model, or honestly more realistically a generalized linear regression model, but let's just stick with linear regression land, you would get this shape. You would get the shape of the age feature explicitly, in the linear regression equation. You have a quadratic here. You have a quadratic equation here, right? You have the x squared and x. You have the quadratic here. You know what that shape is. It's explicitly defined, right? And so that later on, and we'll talk about it some more. That's why they say that you lose a bit of interpretability with some of the fancier models like your neural networks, and when you ensemble things together, when you use GBMs. But your partial dependencies help approximate what the shape looks like. And the reason you have to do that is just because when you ensemble like 1,000 decision trees, it gets a bit hairy as to what exactly is going on. But anyways, I digress. So interpretability is a funny one. When you have a simple decision tree, yes, it is more interpretable. As your decision tree grows, I could argue that maybe things like linear regression are more interpretable. And particularly if you ensemble up the decision trees, I would also argue that you lose interpretability. But again, this maybe they're talking about decision trees, not the ensembles of decision trees. And this is something you talk about later. We talk about later the ensembles. Cool. Yeah, right. So the other thing about your decision tree is that it's a low bias model. So remember, your sources of error just at a very sort of hand wavy sort of level. Very hand wavy level. Ooh, did I just? No, it's still recording. We're in business. I thought. Yeah, cool. Sorry. Yeah. So at a very hand wavy level, your source of error looks something like this, right? And different models will tend to, some models might have more bias, less variance. Some models might have more variance bias. You can do certain things that reduce the variance without increasing the bias. Sort of you win everywhere, well, except it often comes at the cost of computational power. I'm speaking of things like bagging and boosting, which kind of give you a lower variance model and possibly variance bias as well, free of charge. But yeah, typically, like at least the base learners or whatever, right? The base models, you can have like high bias models and high variance sort of models. There's a bit of a trade-off because often higher bias leads to low variance and vice versa, right? Now, typically a model that is more flexible, right? More flexible will give you less bias, right? Remember the bias, you can think of it as some sort of mismatch between the data, like the constructs or relationships between the features and the target. There's a mismatch between that, what's happening in the real world, and what your model is capable of modeling, right? And the more flexible a model is, the more likely, the more capable it in general is of capturing those little nuances we have in real life data. Now, but the problem is if you have a model which is too complicated, too flexible, is that it molds itself too much to the training data, which means that if you sort of just mimic the training data and hug the training data too much, when you swap out the data for another data set, it's going to be wrong. So variance is how much the error changes when you swap out the training data sets, right? So it's often seen as a bit of a trade-off, right? Unless you move into things like bagging, boosting, etc., which help that trade-off. But we're looking at the base learners of what we've seen so far. It's often seen as a trade-off, right? So this tends to be low bias. Decision trees, they're very flexible. Man, they're if-else statements. If you have, just keep adding more if-else statements, you can model possibly many things, right? I don't want to say everything, but you can model so much when you just add more and more if-else statements, right? The sky's the limit in a ways, but of course that comes at the cost of higher variance, right? And the tendency to overfit because you chuck a bunch of if-else statements in and just like the tree could just grow to just I don't know, just huge depth, right? Cool. The other interesting thing about decision trees is that it can give like bumpy or non-smooth predictions. Now what I mean by that is, okay, so this is actually a perfect example in the insurance land. So this might be your typical, say, general insurance motor, your age curve for motor, right? Now, in real life, that kind of makes sense. I mean, maybe you're smoothing it out, but it just kind of makes sense, from a judgment and, just a judgmental point of view, common sense sort of point of view. A decision tree, due to the nature of it, it might do something like this. Right? And sometimes there might be good reasons that there's a sudden step change when you say go from age, I don't know, say 16 to 17, maybe, or 15 to 16 L's, right? And there might sometimes be good reasons, but oftentimes things in real life are not step functions, but we are approximating real life with step functions. So this may or may not matter so much, but this is like a problem which may occur. And this is more prominent in decision trees. If you use, say, GBM, it's going to be more like, it's going to be far smoother, right? Because with, say, GBM, you are ensembling possibly thousands of decision trees, yeah? So if this is a decision tree, possibly some kind of GBM might look more like this. And of course, the other problem is they can't extrapolate. Decision trees can't extrapolate past the data that they've seen. Actually, yeah, that's a good point. Can't extrapolate. I can't spell. This is probably redundant because extrapolation by definition means it's outside of the data you've seen, but just I'm making it more explicit here. And what do I mean by it cannot extrapolate past the data it's seen? Well, what I mean by that is, you see this here, right? Let's say in the data, the maximum age was someone who's, say, 100. Now, the decision tree hasn't seen anything past 100, so the maximum prediction is whatever that guy's age was when they were 100. And likewise on this side. I mean, of course, this is stupid because no one's going to have like an age of, say, -5. But yeah, like, you know, like, so, you can think of some other feature where it might be important to be able to extrapolate, and you know, maybe there's a new policyholder who comes in who's age 105, and you just give them the same as that. But say something like a regression model, you'd fit a curve to it and it'll naturally sort of extrapolate. So that's another little thing. Could be good or bad, actually. I mean, maybe you don't want it to extrapolate, but just something to keep in mind. Nature of your decision trees. Okay. Okay. Decision trees. Excuse me. How to choose on a split. So we went through our first example, and you know, that's all well and good, right? Just choosing all these splits, you know, having all these splits here. But the question is, how did it choose a split in the first place? Now we know with our linear regression model how they went about doing things. So line of best fit, right? Clearly defined. You minimize your sum square error. But here we do something else. And again, I stress this is a classification land. So what the decision tree wants to do, it essentially wants to find the split, right? Which reduces the impurity after the split, right? So what do I mean by that? Every single time you do a split, again, we're in classification land, you want to increase the purity or decrease the impurity. So what do I mean? So look at all these leaf nodes here. They are pure. They're all one class, right? You look at these decision boundaries, right? You want everything to be blue or everything to be red. You don't want this. This is impurity, right? This with impurity. You ideally want things to look like everything else, okay? And so that's the concept I want you to think about with classification trees. The way it chooses its split is it wants to split in such a way that things get more and more pure. Because if you have things which are more pure, it means your predictions, at least on the training data, are probably going to be correct, right? So for example here, this will have perfect prediction on the training data, and so will this. This one, it won't, right? So intuitively, it's the idea of impurity, and every time we want to do a split, we want to make things more pure. But let's make it a bit more formal, right? There's a more mathematical sort of formal definition of purity called Eugenean purity, or entropy, sorry, rather, that I'll talk about on the next slide. But let's have a look at this little example here first, right? And in this example, what we're trying to work out, do we split with this guy, or do we split with that guy? It's kind of hard to say off the cuff, right? Because if I split with this feature, maybe this is x1, I don't know, maybe it's x2. x2 say, and remember that this is the target, x1, x2, right? I can split either way, yeah, and after the split, you know, it's not really easy to tell off the cuff, you know, if how good or bad the split is, right? I mean, I look at this is great, that's a good split. This one, and it's kind of not great. This one's kind of good, this one's not great. That's kind of hand wavy, right? So like, if I had to rate these splits out of 10, maybe I'd give this, okay, this is 10 out of 10, or maybe out of 5. I'd say, okay, you know, this is ace, this is top. You know, this is 5 out of 5. This one is not great. I'll give it maybe a 2. I'll probably give this a 2 as well. Yeah, it's a bit better. I'll give it a 4. This is rubbish. I'll give it a 1. Then you're like, okay, which one's better? Like this one, I mean, half-ish. I mean, like part of the time it's perfect, but the other time it's mediocre. This one, most of the time it's pretty good, but the other time it's rubbish. So I don't know. I don't know. I mean, this is hard to say, right? It would be more obvious if some other split were like, you know, one was like one was like super pure and one was super impure. But this is hard. So let's formalize it on the next page. Let's formalize this concept of impurity. Enter impurity, entropy. So I wanted to sort of give you the intuition about impurity. Now, there's a bit of notation here, right? So this plus is just the positive class. And this is just the negative class. Right? And this is, the P there is, I guess, the proportion. I think it is I mean, they're using, I think they mean as probability, but they're estimating it using the proportion. So this is go proportion. So this is a proportion that's positive class, and that's proportion that's negative class, right? And we have this little graph here, and again, remember this is proportion that's positive class. Just a bit of intuition here, right? Now, it should make sense to you and I that if it is, on this end, if it is like 100% positive, then it's good. We want to give it top score, right? It's great. So, in other words, entropy, remember, is impurity. It's bad. We want to minimize. We want less impurity, right? So it makes sense that on this side, it's 0. There's 0 impurity because it's 100%. It's 100% positive. On the flip side, on this side, you know, if we have 0% that's positive, that means it's 100% negative, right? That's also good. It's also 0 impurity. Okay? In the middle is the worst. This is just like, yeah, it's the worst. So it's like 50%, you know, like positive, but also 50% negative. It's pretty rubbish. It's no good, right? Of course, you can break down the formula, you can plug in the numbers, this and that, but if you were to plot it, I think it'll give you a bit more intuition as to what's happening. Now, of course, you can also generalize this to many dimensions, right? You can generalize this to this is 2 classes, binary classification here. This is binary. This is your binary classification, but yeah, you can generalize it to however many classes you want. And you know, say if it was 3 classes, is that how I do it? Yeah, like a little bowl. Yeah, if it's, I'd say 3 classes, it'll be maximized, you know, when they're all like say at, I don't know, 0.3 repeater, right? And you have some sort of peak, but and then maybe this is class 1, probably a proportion class 1, proportion class 2, something like that, something like a bowl, I think. Cool. Now we've sort of formalized the measure impurity. That's not quite it, right? We now that we can actually measure the impurity at each of these nodes, we can actually calculate what's the impurity here, what's impurity here. It's good, but we need one more thing. What we actually care about is the information gain. Now Now, information gain, think of it as change in impurity, right? Now, ideally, right? Ideally, you have some, like maybe like you'd have, let's say, pre-split. Maybe you have some sort of impurity of, I don't know, I'm going to make it up. Let's say it's got 0.99. Then let's say post the split, after the split, maybe the impurity is, I don't know, 0.1. That seems pretty good to me. You want, I'm trying to illustrate what we want to do is we want to decrease the impurity, right? As much as we can. This is the information gain. Information gain is effectively the change in impurity. I should say negative the change in impurity. It's a negative change in impurity, right? It is the impurity before minus impurity before, after, right? You want to maximize this. Now, in this case, the information gain here is, you can work it out 0.98, which is pretty good. That's probably a pretty good split. And you test this out amongst the other features and other sorts of splits. And then use that to work out where you want to split the one with the most information gain. So think of it as a reduction in impurity of your various splits. The formula's here, right? So you take your original entropy, right? And so that's this guy here. That is effectively maybe this guy here, right? Your original entropy, okay? And then this whole thing here, this is the entropy after the split. I'll explain this in a bit, but effectively you're going entropy at the beginning minus entropy at the end. Now, if it's something like this, if entropy at the beginning is, say, 99.99, sorry, then it's 0.01 afterwards. Sorry, the typo. 0.01 afterwards. You have information gain of 0.99 minus 0.01. 0.01. Sorry. So you have information gain of 0.98, which is quite good. So hopefully that kind of makes sense there. Now, how is this exactly calculated? Now, this is the weighted average entropy after the split. So basically what you do is you look at each split, right? And then you calculate the entropy of each split, and then you weight it, right, by the number of observations, right? So let's say you have like 2 splits, right? You take the original entropy, then you minus, and then you look at the weighted average. You have 2 splits, and then maybe one of the splits has 40% of the observations. Let's say maybe it's 40 and 100, maybe there are 100 observations. Then you give it a weight of 40%. The other split has a weight of 60 and 100, or 60%, and then you weight that entropy by 60%, right? Let's go through an example. Let's make it more concrete. Okay. So in this example, you're trying to work out, which split is better, right? And the way we want to do it is we want to work out, the information gain, which one is better. So let's sort of work it out. Now, the entropy of S, this is the entropy before the split, right? So this is the original. Oh, that's hard to see there, isn't it? This is the original entropy, this guy here, right? And then this is the entropy after the split. So this is, I guess, this is entropy afterwards. Now, entropy, you can use your formula from before, but remember it's just, what is it? Negative. Sorry. you look at all your classes. I think they use K. I forget. Yeah, I'll call it K. Why not? You basically look at the proportions of each class across. So you look at you sum up. You take the negative sum for all your classes of the proportion, of in that class multiplied by the log base to the proportion of that class. Okay, and that's effectively this guy here, and it's the same for both of them. So in the first place 29, which are positive, so 29 on 64, because the sum of these two is 64. Okay, and then you take the log of that and you do the same thing with the 35, and that's that guy there, right? This 0.9936. Then you look at here, right? You look at both splits. This is split 1, A1, right? The left branch, there's 26 guys going into the left branch here, okay? And so then you give it away to 26, and then there's 5 guys, sorry, there's 38, yeah, and then there's 38 observations going into the second branch. So you weight both the splits by the number of observations, and then you'd apply the entropy formula within, and you come to this result. You repeat, you rinse and repeat, and you come to this, and then what your conclusion is, your information gain of split 1 is better than the information gain of split 2. So then therefore so then based on that I'd split based on split using A1. Okay. Now, that's classification trees. What about regression trees? That's a fantastic question. Obviously, in regression land, we can't do things like classes. In regression land, things like proportions, things like entropy, it doesn't really make sense. What is purity? It doesn't really make sense like that. Instead, we're going to use a concept that we're hopefully somewhat familiar with, your mean square error or your root mean square error. And you can use that as sort of a measure of impurity, right? So instead of, in your impurity or entropy, looking at the proportions, now you're looking at, your distance from the mean. You look at your splits, you have the mean, and you look at the sum square error from that mean, your root mean square error, your mean square error, that sort of thing, right? Sorry, maybe I'm jumping ahead of myself. Let us talk about how it works in the beginning, right? So you do splits as per normal. The only difference is that, so your y hat for your in regression land, what it is basically the it's basically the mean at that leaf node. So when you get to the leaf node, you just take this guy here is the sample mean. This is the mean in that leaf node, the mean of the targets in that leaf node, right? And same with all these bars here, the means. You just take the average, and that's a prediction. You split them up, you bucket them up, with your with the if-else statements, and then you take the mean as the prediction. Okay. For example, I think so this box here is this box here, and that y bar there must be 10%. Okay. Or if, let's say the dose is between 20 and 40, which is here. What's the y bar? 12. Wait, sorry. If the what's this one? If the dose is it's 37. So it's 70%. So here that is between this guy here is for when x is between 20 and 37. Inclusive on this side and exclusive on the other side, and in that case there we call it 70%. Sorry, I'm pointing at the wrong thing, aren't I? That's this one there, it's 95%. I don't need the percent, it's already in percent. Okay. Yeah, cool. So as I said before, how do we decide on the split? So instead of impurity, we'll use your mean square error, And what you do is you look at the Y bar, which is the average target value at each leaf node, and then you measure at that node, and then you measure the error there. And quite similarly to your impurity, you look at the weighted average variance, weighted average mean square error, weighted. This is weighted by this is targets, and you want to work out which one is going to decrease your mean square error, which split is going to decrease your mean square error the most. Cool. Let me quickly talk about overfitting. Is that everything? Yep. Let me talk about overfitting. Okay. What is overfitting? Overfitting in a nutshell. So it's when it fits too closely to the training data. You can think of it as a model which pays too much attention to the training data. It maybe fits to the little nuances and the noise of the training data too much. It pays way too much attention to the training data, so that when you feed it a new set of data, it doesn't perform so well because it's learned a bit of the noise. It's only learned the specifics of that training data. The other thing that could happen is you give it a model which is way too complex, and you're trying to feed it the data where the signal is not there. Maybe it's you really need something simpler. Maybe the signal that's there is much simpler, so you don't need such a complicated model. But you give it such a complicated model, it just starts fitting to the noise, and it's not good. Here's an example here. So this is some sort of classifier, and you're trying to work with some decision boundary, right? Now, judgmentally, you and I could probably say that the black line is better. The black line is probably just right. This green line is probably overfitting. Again, it's hard to conclusively say without understanding the data and what it is, but likely this green line is overfitting. And if you were to replace this data with another set of data, then this line might not perform that well. There's ways to prevent. Here's another example, overfitting here. So you just judgmentally, you could probably think, okay, this feels about right. Just using human eye, okay, it feels like there's a pattern which kind of looks like this sort of curve here. Maybe something quadratic-y. A straight line is probably not complicated enough. And why is this less complicated? This could be captured in less parameters. So this could be basically encapsulated in something like this, right? Something like this, you need more parameters. This one here, oh geez, it would just it would go on for a while. I don't know. Let's call it like beta 20. I'm just making it up, right? So you can see here that hopefully why this is more complicated. It is some sort of linear regression kind of model, right? You need far more parameters. As we go this way, the complexity is increasing. Okay, we'll probably agree this is probably the Goldilocks zone. It's right in the middle. Looks about right. Okay, so how do we prevent overfitting? There's a couple of ways. You can use more data. It's harder to overfit when there's more and more data, right? The noise gets sort of washed out with more signal as you chuck in more data, right? And another way to think about it is, when you have less data, when you try to do your bucketing, when you try to sort of split things, there's less data, less observations in each split. It's harder to draw a conclusion. There's more noise, right? And there's other things you can do as well. You can remove nuisance variables or correlated variables. There just might be some random variables and they just don't really do anything. Maybe from a judgmental point of view, if you sort of verified this just through feature importances, you've tested it, you've removed the feature and the model's still about right. There's also heuristics you can use to select features. You can consult with the subject matter expert, right? So for example, if you're building a cancer detection model, you could talk to an oncologist about, okay, now this is rubbish, right? You can use regularization. There's early stopping you can use in a variety of different models, right? You can try a bit of hyperparameter tuning, do simpler models, bagging, boosting, random forest. There's a lot of different ways to encapsulate and to help, sorry, to sort of control overfitting. But just keep these in mind. We'll drill into some of these a bit more. But overfitting is a very real problem, and something you definitely need to deal with in real life. Cool. Particularly for decision trees, there's a whole bunch of things you can do. So there's early stopping. So that what that is it would stop growing the tree when some sort of threshold's met. You could even use some statistical tests to stop building branches if it's not significant. There's hyperparameters you can fiddle around with on the sklearn. Hyperparameters you can fiddle around on the sklearn side. And this is pre-pruning. So this is actually more common in scikit-learn. So pre-pruning is when you sort of, before you build the branch, you just sort of stop. You don't grow the branch, right? If you stop growing the branch, you stop growing the tree at a certain point in time. Post-pruning is you just grow everything and then you trim back later. Now, of course, you can probably work out that pre-pruning is less time-consuming and more computationally, it's computationally cheaper. All right, so yeah, I should probably get cracking. Let's move along to the tutorial questions. Now, what is this? Okay, so effectively, we've got a bunch of Boolean statements, and we are trying to represent these as decision trees. Now, for me, if you're ever confused about any of this sort of stuff, what I would recommend is doing one of these the truth table. Like a truth table going, especially if it's something simple like this. It's quite easy to do. It's not too arduous. There's only two things. The number of combinations is quite small. And say the first one is, what is it? A and not B, right? So A and not B, this is the only time it's true. You just sort of test it out, right? So here it has to be A to these two, and you need not B, so it's on A and not B, right? In terms of coding it into a decision tree, I mean, you can represent a variety of different ways. I've just gone with this sort of typed sort of notation with the indents to signify a new branch is happening, but you can draw it out if you want. Doesn't really matter. Now, based off this, we know that A has to be true. If as soon as A is false, you're done. There's nothing more to do here. So you go true, and then you need not B. So the only option is this guy here, right? We can do the same sort of thing for A or not. What is it? A or B and C. Okay, so A or B and C. Yeah, doesn't matter. So as soon as A is true, then you're good. I don't even need to think further. The other option is if A is false, I need B and C. So I need, oh, there's three things. Let me, add another column. Look, I can't bother doing the decision tree for truth table for 3 if I don't want to do all the combinations, but you get the idea. Let's, I'll leave this here though. Let's just think about it though without drawing it out. Cool. So as soon as A is true, you're good, right? Now if A is false, the only way this can be true is you need B and C to be true. As soon as B is false, you're done. So it looks something like that. Now, XOR, I had a question last week in the tutorial about this. What was it before? XOR means exclusively or, so A exclusively or B. So, maybe I can do it here actually. A XOR B. It's this. So only A or only B at the one time. You can't have both. And also you need one of them. So the only time this can happen is if A is true, B needs to be false. Or if A is false, B needs to be true. This one's a little more fiddly, so you might need to think about it. But there's two ways this can be true. You need A and B, which is what I've squared up, what I've sort of circled up here. Now, if you don't have A or B, in other words, let's say B is false, then the other way you can go about it is you need C and D, which is here. And you know, if that's false, you're done. On the other side, if A is false, this is out of the equation, but you still have an option to get true. You need C and D, which is this one here. Cool. Next thing I'll talk about is next question here. So we've got some data here. This is a target. I don't know why I put a hat there. This is the target, and then these are the features. And you're asked which attributes will be the most predictive of the class, right? And we can sort of use, you know, you can probably use some sort of measure of correlation, blah, blah, but you can look at it intuitively, right? The red square, that's negative class. The green rectangle, sorry, not square rectangle, is a positive class. See if you can find a feature which, you know, in either one it's quite pure, right? What I can see off the cuff is, look, rebel, okay, it's not perfect. If it's home mode is yes, it's always rebel, right? There's some good correlation there, right? Now it's not so reliable on this side, but based off that, to me that would be likely one of the best predictors. Looking at the other features, you want to find something which is just fairly, you know, this is different, right? On the no and the yes target. Now what you see here is that if you're diamond or jasper, you are yes, right? Diamond or jasper only appears here. On the flip side, things like garnet, bismuth, and bismuth only appear on the no side. So you know, I'll probably say, you know, your species and your rebel, whatever that means, is the most predictive sort of class. Okay, so the question then is, how do we sort of measure this, right? We can use our information gain, you know, as we learned before in an earlier slide. We can calculate the two of them. But then what if they're told, actually, interestingly enough, both of these guys, the information gain for your species and your rebel is quite similar. They've calculated for us as 0.52 and 0.48. Then you're like, okay, it's kind of similar. What do I do? Look, I know that species is higher, but wait, hold on a minute. I remember in the lectures, Mike told me that that one of the downsides of information gain is that it biases features with more levels, right? So, because the intuition there is that the more levels that you have, you know, the more specific a split you can have, you know, the more likely you can, you know, cut things up so that things are pure, right? If you just have two levels, and you know, it's you don't have that much options, not much flexibility there in terms of splitting it in a way which is pure. There's something called the gain ratio, which you can think of as a sort of bias correction of the information gain, so that you don't, you know, always bias the features with lots of levels. It's a correction factor, right? You take your original information gain and you divide it by what's called your split information. What split information is split information. This should look familiar. This kind of looks like entropy formula, isn't it? Doesn't it? You're correcting this effectively by this is literally the entropy. This is the entropy in terms of the number of levels, right? And so the idea is, with the split information, the more entropy there is, the more you divide it by. In other words, greater entropy, or I guess greater number of levels, means you have greater entropy, which means that the gain ratio will decrease. You're penalizing the gain ratio by the number of levels. So this is entropy, and this is a penalty for higher levels, higher numbers of levels, right? If there's fewer levels, then it's good. This will be less of a penalty. So all you have to do is you plug it into the formula to work out the gain ratio here, right? You know, and then after you calculate, you realize, okay, actually, the gain ratio of Rebel is 0.49, but the gain ratio of Species is 0.21. So after correcting for the bias in information gain of the number of levels, you realize actually a Rebel is better. So we go Rebel here. Next question. So assume we learn a decision tree to predict class Y given attributes A, B, C from the following training data set with no pruning. What will be the training set error for this data set? Express the answers, number of examples out of 12 that will be misclassified. Now, let's assume we have a decision tree that can, you grow it to however big you need, right? However many trees you need, you just grow it all the way. So long as each combination of features is unique, right? You can map it to the correct, at least on the training data set, the correct target. So the trick for this is just go through all this and find like where there is a unique combination, where there's a combination of features, but the targets are different. For example here, if you're a decision tree and you're only given these features, right? There's no way to differentiate these two. This would always generate an error. These other ones are fine because they're unique, right? And like even though these two are the same, say, right? Feature-wise, the target's the same, so it's fine. The only other time this happens is here, where the features are the same, right? So in this case, the x whatever is equal to the x. The features are the same, but then unfortunately the y is not equal. The target's unequal. So then the question is, for both of these, what do you set as y hat? If you set it to 0, you're going to get 1 wrong. If you set it to 1, you're also going to get 1 wrong. And same down here. So basically, out of all this, the minimum error you'll get is your 2 out of your 12. This is the minimum like classification error out of your 12 out of your 12 data points, right? So it's 2 here. Cool. The next question, there's quite a few questions. The next question is, decision tree learners can do your multi-class classification, right? You can do, not just binary, like, alive, dead, claim, no claim, you can do multiple, like you could do, say, blue, red, green, that's 3 classes. You could do, say, tuna, salmon, sea bass, that's also 3 classes. You can do some positive integers as a number of classes within reason. Now the question is, suppose you have a decision tree to be learned on an arbitrary set of data. What is the maximum training set error as a fraction that any data set could have? So when they say maximum data set error, just think of like the worst possible model you could have. The worst possible model you could have, that's kind of reasonable, is you have a stump and like your y hat is just the majority, it's a constant. It's just the majority class. Now, of course, you could have an even worse training error by going y hat is equal to the minority class, but that wouldn't even make any sense. It's just, why would you do that, right? So, assuming some sort of reasonable stumpy tree, where your prediction is always a constant, right? If you always predict at the majority of a class, right? And for a moment, let's just assume that everything's uniformly evenly distributed in terms of the classes. Then if you vote for the majority class, this will be worth 1/k of the data, right? So in other words, your accuracy is going to be 100% minus 1 minus k, which is the same as k minus 1 on k, which is what this thing is here, right? Now, then if any one class is more than 1 in k examples, then that worst decision tree is guaranteed to predict that class, which will mean that the error will reduce. So then if any class has more than 1 in k, it will be less than that. So this will represent a maximum bound. So this will represent a minimum level accuracy, right? So if any class is more than 1 in k, that will be the majority class, and then it'll be greater than this accuracy. This represents a minimum bound based on the logic in this last line here. Next question. So model tree. In learning a model tree, Okay, so what is a model tree? I want you to think of it as it's a decision tree, right? But instead of like your prediction being the majority class, your prediction in your model tree becomes another model. So it could be like, then you have like a linear regression model here, right? As a prediction at the leaf node instead of like just the majority class. So what is happening here is if you don't really understand model tree, you can have a look at the lecture slides again. But yeah, effectively it is a decision tree where your leaf node is another model, right? Instead of just like a straight up prediction. Now, the simple example there here is, you have, let's say this is a decision tree, you have your root node, which is a linear regression model, and then you go down a node and it's another linear regression model. You have like models. That's why it's a model tree. You have models at each of your nodes, right? And in reality, it could look something like this, right? You have a decision tree which splits, let's say in this example, on x equals to 2 and x equals to 10. So if the first split is x less than 10, okay, then you 2x plus less than 2. There's a typo here. So your first split could be, if x is greater than 10, you'd use this linear regression model. Otherwise, if it's less than or equal to 10, maybe you use, maybe consistent. If it's less than 10, you'd use, you split again and you work out whether it's this model or this model. But either way, there's always a model, right? It's a model tree. Now, the question here is we can apply a bit of smoothing to the model tree, okay? And you're effectively told, right? You're effectively told what the actual target function is. The actual target function looks something like this. Well approximated by something like this, right? What the smoothing does is you've got like models at each node, and you take a bit of an average, a smoothing average between what's at the node and then the prediction at the leaf. So you don't just jump straight to the leaf. You sort of smooth out, between the root and the node. So the question is, has smoothing improved the prediction? So the smoothing formula used has been placed here, right? And it's a weighted average between, and you look at the number of observations in the root and the leaf, and you smooth out the prediction between the root, and the node, and the leaf, sorry. Okay. Yeah. So, yep. So you plug it into the formula, and it's basically set up like this. So you're told that there's the root node of 1.5x plus 1, and then there's a split condition on x is less than 2 or greater than 2, and you have 2 more models. And then so let's say, and then you're told a few parameters. Basically, you just got to plug it into this formula here to work out what your p dash, which is your smooth prediction. So what you do is you plug it into here. So your p dash is np and n is the number of observations down here at the split. So here n is equal to 2. You only have 2 observations down at the split. 11 is this guy here. It's a prediction at the leaf node, right? And then take kq. Q is a prediction at the root node, which is 4 here, and k was the number of observations there. Your smoothing factor was 5. You take the weighted average and you work, okay, your smooth y hat is 6. Remember your unsmooth y hat, originally what was it, 11? He asked here, has smoothing improved the prediction? Yes, because we actually know the real target value is 5. We smoothed it, became 6, and before was 11. Yeah, it's better. Cool. Extended tree learning. Propose an algorithm to extend the decision tree with naive Bayes classification. So there's extension, so don't worry too much if you're not fully across this. But effectively what's happening is here, let's say I have a very simple decision tree and you have two classes, your orange and your green. You do split as per normal, but the idea here is use naive Bayes as an alternative to information gain as to whether to decide information gain as to whether to split using that or not. You use naive Bayes and you look at and then you use, say, the cross validation score, right? So you here and you calculate your naive Bayes CV score. Maybe it's, I don't know, 85% here, and then maybe the let's say you know, you take the weighted average between these two splits, 85%, and then maybe compared to some other split. And actually, maybe the accuracy here was 245. Was it 2468? So it's a 5. Yeah, do I want that? Yeah, so 60. So let's say 62.5%. Okay, so here, right here, if you use a prediction here, you predict the majority class, it just be 62.5%. Let's say you use naive Bayes and you split it, and let's just call it 85% or something, make something up across these two. Then you want to do that split. But the key idea here is you're using naive Bayes as an alternative to your information gain. Cool. Next question: how could you combine tree learning with local regression as described on slides 101 105, right? So as I touched on before, it's kind of like your model tree. So what you do is something like this. So instead of learning, instead of using, like, say, the majority class or the average, right? You effectively fit a linear regression model at the leaf node. So if you used your stock standard decision tree, it'll be something like this. Your y hat for, just say, your normal decision tree would look something like this, right? But the green is the y hat. If you use let's call it the regression model tree. Let's call it regression MT, regression model tree. Okay, so remember, with the decision tree, this is effectively the y bar, the average in this bucket. This is the average in this bucket. This is average in this bucket. You can combine the two and effectively fit a linear regression model in each of these splits instead of just taking the average. Cool. Next one. Okay, so what they're saying is when you're trying to search for the best splits, right? It's going to blow up computationally. It is known to be what is it? NP, non-deterministic polynomial complete. And the most common solution is some sort of greedy search. And they're just saying, suggest how we could do some sort of greedy search to go about doing this. Now, you might remember your tree searches. These are decision trees, so of course you can use your tree searches. Your depth, and what I want you to think of it, in this case, the path cost. You know, when you do your path search, shortest path, whatever search from decision trees, your path cost here, you can think of it as some sort of maybe the mean square error, right? You go along the path, or maybe some sort of measure impurity. So that's your path cost here, and you kind of want to minimize that, right? You want to split which minimizes the mean square error, okay? Depth first search, the problem with that is it's a bit dumb. You just drill all the way down. You're probably going to waste a lot of time on non-minimal paths, which have a high MSE. Now, you might want to use something called breadth. You might want to use a breadth first search. A breadth first search, sorry, just it doesn't look at the path cost necessarily, right? But you can use, say, you can use a beam search, which is an optimized breadth first search, and what it does is it keeps a list. It's greedy in the sense that it keeps, prioritizes searching down the paths which have, I suppose, a lower path cost or lower level mean square error. But a beam search is even more optimized in this case, which is what I'm talking about here. It only keeps a list of, like, the top end, say, paths to search down, right? But you can think of these as as some sort of a tree search, as with a path cost with mean square error and impurity, right? Yeah, and the suggestion there is your depth first search. Obviously, you can get a bit more complicated. You can have some heuristics and stuff. It might have to be pure greedy search, but that can be what is quite common. Cool. That's not it. Alright. How am I doing for time? Sorry, it's a little rushed. This week, it's been a hectic week. I've got to run somewhere soon. But, feel free to jump onto the console and ask me to drill into anywhere which is possibly a bit unclear. Okay. So the notebook. So we've got the Titanic data set again, and effectively what we're trying to do is we're trying to, build a decision tree from scratch. We're trying to build a decision tree from scratch, right? The first step is, we've done the exploratory data analysis in the weeks before. So just to remind you guys all again, all these sort of doodles here, they are in the slides. So they are being uploaded here. So if you go to that link that I always share, you'll be able to find all the slides there with all of the doodles that are made on top of it. Sorry, so back here. So one thing to keep in mind is that in general, in sklearn, a lot of machine learning algorithms, it can really only handle numbers. You can't just feed it like male, female, like text categories. You certainly can't feed it just free text. Certainly can't feed it free text without any sort of processing. You need to do whenever you have some text categories, you need to do some sort of pre-processing. So things like gender, and there's quite a few different ways. There's one-hot encoding, there's ordinal encoding, there's a variety of different ways. In this example, the only features we're considering are these ones, and we probably only really need to look at what's called one-hot encoding for the gender. Now, something like this is free text, and it could get quite hairy. You can extract features out of that using, say, maybe some sort of regular expressions, some sort of pattern matching. Maybe extract, what is that? Misses, doctor, you could extract features out of that possibly. And if it's a bit more of a free texty, even more free texty, you could consider some sort of natural language processing to extract features. But in this simple example, the only one we really, really, really need to care about is we're only looking at these features, right? And the only one that in here that needs to be converted to a number is sex. Now, your P class, luckily, it's ordinal in the sense that one-hot encoding gives every level its own field, but ordinal encoding, it gives it all a rank of sorts. This can be interpreted as a rank, and luckily, passenger class is a natural sort of rank interpretation. And that's one of the problems of encoding features as just ordinal values, because the sklearn, the machine learning algorithm, just see it as maybe there's some relationship. Let's say code this is blue, green, red, right? It's not that blue is 3 times more than red, but it's just coded that way. But luckily here again, we there is some relationship between class and the number, so that's fine here. Okay, there's one-hot encoding, so we just coded 1 as 0 and female is 1. Else return, yes, cool. There's some missing data in the data set. Now, missing data imputation is quite important. A lot of machine learning algorithms can't handle missing data off the cuff, and there's quite a few different ways you can perform what's called your missing data imputation. Common ones include using the mean, the mode, the median. You can also use what's called model-based missing data imputation. That is, you do round robin style. You ignore you fit a machine learning algorithm, and the target is that feature with the missing data, and you backfill it that way. So that's an interesting thing to do as well. But again, depends on the complexity, right? There's other smart ways you can do, smart things you can do about that. You could also just drop if there's not too many, you could possibly drop the observations that have missing data, right? Or maybe even the columns. There's a lot of judgment in play, and it kind of also depends on how much data you have. Possibly also missing data might carry information. Maybe missing data should be coded to another level, and then that allow machine to pick up any signals, should there be any. Correlation heat maps are quite useful, right? They allow you to quickly see links between the data or relationships between the data. Often the most important one off the cuff is to look at the target, which is survived, and to see what it's linked to. So what you can see here is survived is here. Now, it is negatively correlated with age, so you're more likely to survive if you're younger, fine. Now, sex, it is, what is that? positively correlated. So remember, one was female is number one. So if you're female, you're more likely to survive. Again, that's consistent with, if you've seen if you've seen the movie The Titanic, or you probably noticed that. I mean, it is somewhat historical. I mean, what is it? Women and children first, right? That's how they did things in the lifeboats. And what is this? So this is negatively correlated. So if you're class number one, you're rich, you're more likely to survive. And that's nice. You can also see correlations between the features as well. This is nice to sort of get a handle on the data. If you get a bit more hands-on and you want to fit features manually and try interactions, then this could be even handier. But for the time being, I think it's just nice just to get a feel of what's going on with data. I mean, this might pick up any errors. For example, if you see like something funny, like, oh, why is it that males are more likely to survive? You're like, wait, I know the Titanic, the females survive more. Then you might play the data and realize, oh, there's a data error. So this can possibly help identify issues in the data as well. Cool. So you've encoded this way. So this is the usual way we encode it. Y is a target. Capital X is a design matrix. It's capital X because it's a matrix, a design matrix of the features. Cool. This is where we do our we build our decision tree algorithm. This little handy helper function lets us split the data based on some key, right? So if it's above or below that sort of F key, we'll split it left and right, create a tree. Entropy we've already talked about before. Remember the formula, you look at what is it? So negative, the probability, the proportion of that class, and then the log base 2 of that class again, and you've got to sum it all up. This is summation. You're just cycling through all the classes and incrementing it. Remember, information gain is a change, right? So that you change in entropy. So original entropy minus. This is the weighted average entropy after the split, right? Weighted average entropy after the split. So entropy before the split, entropy after the split. You want to look at the change in entropy, right? Negative change in entropy. The more the entropy drops, the more information gain. Good. Here's decision tree object. So this is a bit of a, not it's a bit, oh, I was saying recursive, but this object will store more trees in itself. So, if you have a decision tree object, then, your left and right branch is another decision tree object, and you sort of recursively go down the tree that way, and it stores a few other things as attributes. The key, the value, this is for the prediction, and the max depth. So let's go about how we train the decision tree. So we have a list of features, right? And then you cycle through all the features and you test out the information gain for the features. Now the key thing to keep in mind here is we're splitting based on the mean. Now if you want to do this maybe in a better way, you might want to test, but again, it's a small data set, so it's fine here, but you might want to test out splitting not just on the mean. You might want to split a variety of different ways, but anyways, this is fine here. You're cycling through all the features and splitting based on the mean, and then you have a list of information gain. Then you look at the maximum information gain from all the features, and you want to split based on the information gain, split based on the feature which gives you the greatest information gain. You split the data, right? Now here is this is funny bit. So effectively, if you've reached a leaf node, in other words, you got nothing left, there's 0 rows left, you add a leaf node, it's time to predict. Otherwise, there's a parameter called max depth, how many branches it goes down. If you've hit that, then okay, we're done. Let's predict based on what we've saved as the self dot target. This is where we recursively build the tree. So you keep building, right? And of course you got to track the depth parameter, so you stop building when you hit the max depth, right? Cool. And the prediction is if tests, so predict, you basically go down the tree based on what's happening with the features, and then when you get down to a leaf node or you hit max depth, it will return the prediction. Cool. And next thing you do is now we test it out. So we instantiate our decision tree and we train on our training data. This is some text output to show you training. And then we test it out. So these are the first couple of splits. If it splits on passenger class, the average, then the age, sex, age again, and passenger class just keeps splitting. And then you test it out. You look at the first 10 predictions. You look at the predictions and you compare it against the actual data set, and you have an accuracy of 80%, which is pretty good, right? Now, of course, I'm sure you're aware sklearn itself has its own decision tree classifier, so you can also use this as well. And actually, our custom classifier outperformed. You can play around with some hyperparameters, maybe get something better. You also have your random forest classifier. Perhaps we'll talk about it next week, but the random forest is basically a bag decision tree, but each bag decision tree gets a random subset of features in order to decorrelate each decision tree, therefore increasing the variance reduction effect of your ensembling bagging method. Sorry, that was a mouthful. I will talk about it more later, but yeah, this is a decision tree, your vanilla one. This is an ensemble of decision trees of sorts. You've bagged it and done some other things. Cool. Right, so that's all for today. So I apologize, it's a little bit rushed. That being said, it's still almost an hour and a half, and tutorials normally an hour. But yeah, feel free to jump in on my tutorial sessions Monday 6 to 8 or Thursday 7 to 8. If there's anything I missed here, got some questions, come along, have a chat. You can ask me about what I do at work. You can ask me about any of this sort of stuff. Ask questions. Cool. Anyways, hope you guys enjoy this and have a good rest of Sunday and a good week. See you guys. Thank you very much.